Good morning, everyone. So, welcome to my YouTube channel, Maths Spectrum. So, today we are going to see second lecture on image still yet integration. Okay. So, let us start today's session now. So, in last lecture, we have defined UPF alpha and LPF alpha. Okay. Now, I want to write a remark on it. Now, if I will take, we have this one, UPF alpha, and we have defined LPF alpha already defined in previous lectures. In previous lecture. Okay. Lecture number 2. Okay. Previous lecture. Now, if we take alpha was monotonically increasing. Now, take alpha x is equal to x. Then this is monotonically increasing from closed interval AB to R. That is monotonically increasing. Then what we have? Then delta alpha I will become delta xi. In this case, what is UPF alpha? UPF alpha will become UPF and LPF alpha will become LPF. Okay. Okay. Now we are going to prove an important result. You can say theorem. Let F close interval A B to R be a bounded function and alpha close interval AB to R be a monotonically increasing function then for any partitions P and Q of closed interval AB, we have what we have what we have L P F alpha is always less than equal to L LPF alpha is always less than equal to U Q F alpha. Okay. So let's see its proof. So we have okay. So you repeat the same proof. Replace delta xi by you replace xi by alpha I xi for I goes to 0, 1, 2, 3 up to n, and delta xi by delta alpha I for in the proof of LPF less than equal to UQF. This proof has been done in Riemann integration lecture 2. Okay. So you see that proof and you replace xi by alpha xi and delta xi by delta alpha. Okay. And repeat the same proof. Repeat the same proof. Then it will be proved. Okay. In the proof of LPF less than UQF, you replace xi by alpha xi and delta xi by delta alpha and repeat the same proof, you will get its proof. Now observe one thing. So now I am writing a corollary. Let f close interval AB to R be a bounded function and alpha close interval AB to R be monotonically increasing. Then M alpha B minus alpha A is less than L P F alpha, that is less than U P F alpha. U Q F alpha less than capital M times alpha B minus alpha A. Okay. Okay. This happens. How? Let's prove it. We already proved that. So this happens for any partition P and Q. So I should write there for any partition P and Q of closed interval. Okay. Let's prove it. So its proof is simple. By previous lecture, we have m alpha b minus alpha a is less than LPF alpha less than UPF alpha capital M times alpha b minus alpha a. Okay, now you take this one only. This implies M alpha b minus, okay, less than LPF. Let's say this one. Okay. Now again using previous lecture, okay, again using previous lecture, we have m alpha b minus alpha a less than equal to LQ, because Q is also partition, so this will hold, because Q is also partition. In place of P you can take Q. Q is also partition, P is also partition. If you replace P by Q, it will same thing will hold, because this is result is true for any partition. Alpha b minus alpha. Now combining, you take only this much part. What you will have? QF alpha less than capital M times alpha b minus alpha a. Now from 1 and 2. Now by theorem what we have? We have LP F alpha is less than UQ F alpha. LP F alpha is less than UQ F alpha. Now from 1, 2 and 3 we get, no, from 1 what we have? We have M alpha b minus alpha a, that is less than LP F alpha. Okay, by equation 3 we have this one. You have alpha. Okay. Now by equation 2 what we have? This is capital M times alpha b minus alpha a. Okay. So this is proved now. Okay. So today's lecture up to this. If you have any program related this, you can comment on my YouTube channel. Like, share, comment and subscribe my YouTube channel. Thank you very much for today's lecture. Thank you.